In this video, we're going to work through a little bit more difficult function in that it is a rational function such that we're going to try to find the first derivative. And in working through this, we've learned that if it was just the numerator, we would end up with a polynomial of x to the fifth minus 2x minus 3. We know that the properties of derivatives allow us to separate these. Anything by addition or subtraction, we can separate and find the derivative of each individual term and then combine them. So in this case, we know that minus 3 is going to be 0. So we would have ended up with, we'd bring the 5 out front. So 5 times x to the fifth minus 1 minus, and we would end up with just 2, and we'd be done. So those are very, very easy to find, to solve down. And for a rational, though, we need to remember that the denominator means that each term in the numerator is being divided by 3 times the square root of x. In remembering that, we can then rewrite this. So if we're going to take the derivative, find the first derivative of this, we would say, and another notation for this is simply that y apostrophe, that's saying find the first derivative. And then we would write this as y is equal to, and we could rewrite this, x to the fifth minus 2x minus 3 over 3 times the square root of x. Let's go ahead and just separate this out first. So let's create fractions, individual fractions, as x to the fifth over 3 times the square root of x minus 2x, again over 3 times the square root of x, and then minus 3 over 3 times the square root of x. So at this point, let's take a look and see if there's anything immediately that we could reduce. And we know that 3 over 3 here is going to reduce down. So we're going to have really 1 over the square root of x. Next, our general formula states that we would need, and we wrote our general formula as the derivative of d with respect to x such that x is in the numerator, so x to the nth, and that this is the formula that is essentially n times x n minus 1. Well, we have in the denominator a square root x. We need to bring that, or somehow create that x as a value that is no longer in the denominator. So that's the first thing we should do, is figure out how to bring that square root x up to the numerator so that it's in a standard position. Going back to our basic algebra of powers, the rules of powers, we could begin by just rewriting this as 3 times x. And anytime you have a square root normally doesn't have the 2 here, but anytime you have a square root, that is x, that's the square root of x to the first power. And you bring that 2 under that power such that x to the 1/2 is writing the square root of x. That's the same thing. It means the same thing. Since it's in the denominator, since it's down below in the denominator, if we bring it up to the numerator, we would write negative. We would write it as x to the negative 1/2. See, that's how you would write that. So before we jump too far ahead, let's just go ahead and rewrite that square root as x to the 1/2. So minus 2x over 3x to the 1/2 minus 3. And we've already reduced this, so let me correct that and just say that this is minus 1 now to the x to the 1/2. Anytime that we have a fraction by a common term with an exponent, the rule for that is such that if you have x to the 5th, just x to the 5th divided by the square root of x, which is x to the 1st over 2, so x to the 1/2, we simply write it as x in the numerator to the 5th minus whatever is in the denominator, so minus 1/2. And of course, then we need to make sure that we have that written in a proper fractional form with the same denominator. So it would be to make sure that 5 is raised up to the second, or I'm sorry, that 5 is over 2. The only way to do that is we end up with 10 over 2. That's the same ratio. 10 divided by 2 is 5, minus 1/2. And that's going to give us 9 seconds. So that's how you do that. So you don't have to rewrite this again as x to the negative 1/2 in the numerator. So you wouldn't have to write x to the 5th multiplied by x to the negative 1/2 over 3. You could, but you don't have to if you remember those rules of powers from algebra. So let's keep going here. And we found out that x to the 5th over x to the 1/2 is going to give us x to the 9 seconds. These have been combined, and now we have x to the 9 seconds over 3. And let's continue rewriting this with lead coefficients here. Let's go ahead and write this as 1/3 x to the 9 seconds. So that's how we're going to write those. So we break this apart into separate fractions. We can reduce any terms right away. And so we're going to separate into equal fractions or rational functions. Let's call them rational terms. And then we can reduce. And then we're going to rewrite this by combining our variables to powers, reduce. So we're going to write this as minus 2/3. And then we're going to look at just x over x to the 1/2. So we're going to have x to the 1st minus 1/2, which is equal to x to 2 over 2 minus 1/2. And that's going to give us a positive 1/2. So we end up with x to the 1/2 in the numerator there. And that's going to be minus, and then we have 1 over x to the 1/2. So in this case, what we can do is just write 1 times x in the numerator to the negative 1/2. So this way we can just bring it up to the numerator so that it's in that general form. So here we're going to combine variables, of powers, and I should say like variables. Obviously, if it was a y in the denominator, you don't combine that with an x variable. So next, we can finally begin using what we know about derivatives for each one of these terms. So we know that it's going to be 1/3. We have 1/3 as a lead coefficient. We're going to bring that power down, that 9 seconds. We're going to multiply that by 9 seconds. And we're going to have x to the 9 seconds. minus 1. And that's going to give us 9/6, which reduces. So we're actually going to end up with 3 seconds or 1.5. We'll just write it this way as an improper fraction. And then we'll deal with this 9 seconds power minus 1. So that's the equivalent of 9 seconds minus 2/2, which leaves us with 7 seconds. So we'll have 3 seconds times x to the 7 seconds power. Getting ridiculously hard to say that over and over. All right, minus, and we're going to have 2/3 multiplied by 1/2, and we can start separating these out just so they make sense. Multiplied by x to the 1/2 minus 1. And so that's going to be equal to 2/6. And of course, that reduces as well. So we're going to end up with 1/3 times x, and 1/2 minus 1 is the same as 1/2 minus 2/2, which is going to give us a negative 1/2. And finally, we have minus our 1 multiplied by, we have to bring that power down, and it is a negative 1/2. So we're going to have 1 times negative 1/2 multiplied by x to the negative 1/2 minus 1. And again, we'll bring that down, and this is going to be negative 1/2, which is the reason that I make sure that at this point I want to be consistently bringing my brackets down, whether you're using brackets or parentheses. Make sure you separate those, because you can see that we're eventually going to carry this through, and it'll end up being plus 1/2. So then we have times times x to the negative 1/2 minus 1. So that's negative 1/2 minus, and we will say over 2/2. So that's going to give us a negative 3 seconds. So we have, and we bring that down, we have negative 1/2 multiplied by x to the negative 3 seconds. And let's go ahead and simplify that a little bit. And the general rule is as it was given. So we have an x in the square root, rather than it being written as in the denominator, rather than it being written x to the 1/2. So we're going to simplify it back to that form. So let's go ahead and simplify this first. We have 3, and x is in the numerator here because it's a positive power. So we have 3 to the x to the 7 seconds over 2 minus 1. And because x is to the negative 1/2, we're going to put that down below. We're going to have 3 times x to the 1/2. And that will be plus, we're carrying this through, and that will be plus 1/2. So that's 1 over 2 times x to the 3 seconds. And remember, when we bring the x back down to the denominator that has a negative power, you can change it back to a positive power. So let's further reduce this by showing it as 3 times 3 times the square root, the denominator of a power fraction. So we have 7 seconds. Write this a little better here. 7 seconds. This is the actual exponent power of x. The denominator denotes the root. So if that was a 3, it would be the cube root of the cube root of x. In this case, it's 2. So that's going to be the square root. Oops. So that's going to be the square root of x to the 7th power. And yes, you can, if you're wondering right now, before I move on, just remembering from basic algebra that if you have it to the 7 seconds, so that's x times x times x times x, blah, blah, blah. And each one of these are square roots. Well, for every 2 that you're multiplying, so you have the square root x times square root x, well, that just gives you x. So another way mathematically to look at that, rather than pictorially, we could say that 7 divided by 2, not square root, so used to that. So 7 divided by 2, and that will go in there 3 times, right? And we have a remainder of 1. This tells us that we will have x to the 3rd with 1x square root. So x to the 7 seconds can be written as x to the 3rd times the square root of x. So it can also be written that way. We're probably not required to take it that far. I would say that once you realize what kind of a root it is, go ahead and write 3 times the square root of x to the 7th over 2, and you should be fine. So let's go ahead and finish this up. We're going to end up with 1 over 3, and this is just simply x to the 1st power, so that's really just the square root of x, plus, so that's going to be plus 1 over 2 times the square root of x to the 3rd. And because our original formula had that square root of x in the denominator, do not worry about rationalizing this expression. So don't worry about that. This will be fine. Later on, when you're dealing with a much longer string, and or you're combining or different things like that, it might be to your benefit to eventually combine this back into a single expression, but you would then need to make all of these denominators equal. So that would take some time, and at this point, we're not required to do that. All right, well, thanks for watching. Hope that helps.